All right. So yesterday, when we looked into the subject of electrons, the subtopic of electrons, the first thing that we looked at was the idea of thermionic emission. Okay. So the words thermi, and then onic, therma, and then ionic, and then emission. So it is the release. Emission is the release of electrons. Okay, from a heated surface. Thermionic emission, the release of electrons from a heated surface. Now, the heated surface is not necessarily a flat surface. It can be a filament. Okay, it can be a filament yang berpusing-pusing kan. It's still a heated surface lah, And so when a surface gets heated what happens is that the free electrons, electrons that are usually at the valence, the valence orbit lah, orbit ka itu. Okay, so the valence orbit, they are usually what we call the free electrons. They are a little bit more free, and they will get enough energy to overcome the pull of the nucleus, and so they will be free. Okay, and the idea is that if they are free, they need to go somewhere lah. You can't just free somebody and then like lepas tu tiada hala tuju dalam hidup lah. So what we do is once we let them free, okay, so they will gather at the cathode lah, okay, which is a negative terminal, and we will draw them towards the anode. Okay, and we not only draw them, we give them an acceleration. Okay, we give them an acceleration by giving them like another boost lah. Okay, macam satu boost atau apa itu, kalau orang racing car bahkan kita panggil apa, NOS ka itu, NOS. I don't know what that NOS stand for lah, but yeah. So we give them some sort of NOS or some sort of acceleration, okay, in the form of extra high tension. And generally extra high tension is about 3 to 5 kilovolts lah. Okay, so it's a lot of electrical energy that is being provided to the electrons so that they can accelerate. Okay, and we have seen yesterday in an electron gun, okay, such as this, okay, if we extend the distance further, the electrons are going to move in a straight line, okay, and they're going to finally hit a screen which is made up of this material called pentafloor. Okay, so the pentafloor screen is going to give a green color effect, and we will see something like that a little while later lah. Okay, but the idea that we saw yesterday, and I hope that you remember this from yesterday's video, okay, is that this is what we call a cathode ray. Okay, when we accelerate an electron, or when we accelerate, when we accelerate a row of electrons, okay, they're going to form a ray, and the ray is what we call a cathode ray. Why is it called a cathode ray? Because it originates from the cathode. It's being pulled by the anode and accelerated also by the anode, okay, with an extra high tension so that it finally hits the pentafloor screen. So today, we need to talk about how the cathode rays are affected, okay, by an electric field and a magnetic field. So cathode rays, they don't just travel straight. I mean, they travel straight unless you introduce a new element. Okay, so we're going to talk about these two new elements, which is, what if we put a cathode ray inside an electric field? Or what if we put a cathode ray that is traveling straight? Okay, originally the cathode ray is always traveling straight. So what if we put the cathode ray inside an electric field? Or what if we put a cathode ray inside a magnetic field? Okay, what will happen to the cathode ray lah? So that's what we want to look at the next part. Okay, so remember, originally it's always straight. But once you put it inside the field, something happens. So we can do that, okay, by looking at these two alat lah. So the first one is called a Maltese cross tube. Okay, the one on the left here is called a Maltese cross tube, because inside over here there is a shape of a cross over here lah. Okay, so yeah, this cross is not the Salib cross. This cross is just like, like X marks the spot kind of cross lah. Okay, like crossroad kind of cross. So this is called a Maltese cross tube. Okay, I don't know why it's called a Maltese cross tube. Maybe because somebody in Malta discovered it lah. Maybe I don't know. Okay, but this is a Maltese cross tube. Okay, and this is a deflection plate, a deflection tube. okay, tube pemesongan, is called a deflection tube. Oh, okay, it's not in your edition. But anyway, I just want you to see lah. Okay, so the Maltese cross tube, there's just a cross in the middle here. But the tube pemesongan, the deflection tube has a plate over here lah. Okay, but what is interesting is that the deflection tube, there are two outlets over here. Manakala, the Maltese cross tube only has one. Okay, so we will look at it a little bit later. But the characteristics of the cathode ray can be studied by using these two. Okay, so let's get down to this now. What if we put the cathode ray, okay, inside a Maltese cross cathode ray tube? Okay, so we have the same thing over here. Okay, we have the electron gun. This beginning part is the electron gun lah. Or actually, this whole thing is the electron gun, but we put a Maltese cross inside. So now it becomes a Maltese cross tube. Okay, so originally, what's going to happen is normal when we turn on S1, okay, there's going to be thermionic emission. Okay, and you're going to have all the electrons gathered around here. And then when we turn on S2, you're going to have this EHT power supply, which is about 3000 volts, okay, generally, yeah. Okay, and we're going to have the electrons are going to memecut, okay, they're going to accelerate past the anode, and they're going to supposed to hit the screen lah. Okay, but what do you think happens to the electrons that hit the Maltese cross tube? Anybody want to guess? What do you think happens to the electrons? Okay, so the electrons that are, like here, of course they will hit this. Of course they will hit the screen. Okay, what do you think happens to the electrons that hit the Maltese cross tube?
The electrons stay at the cross.
Okay, the electrons stay at the cross. I think that makes a lot of sense. Yeah lah. How can you pass the cross? And how can you pass the cross if it's right in front of you, right? I mean, the electron doesn't have that much power. It can't make a hole at the cross. Okay? I think that's a very logical explanation. Same thing like you, lah. If you are being pushed on a trolley directly into a tree, right, and you can't stop yourself, of course you're going to be stopped by the tree. Okay, you're going to get into an accident with the tree, lah. And that's exactly what happens. Okay, so you're going to have, first of all, when you get a 6-volt heater supply, okay, we find a shadow of a cross on the screen, but there's a yellow light produced on the screen because at this point in time, S2 is not turned on yet. Okay, so why is this happen? The shadow is formed because the light from the filament is blocked by the Maltese cross. Okay, but and this proves to us that light travels in a straight line. So even though, okay, at this point, in procedure number 1, when you turn on S1, so the 6-volt heater supply is connected, so only S1 is on. Okay, S2 is off. Okay, S2 is off means it is not accelerating. That means the electrons that are here, okay, are naturally going to be pulled towards the anode, but it's going to be pulled without an acceleration. So you're going to find a yellow light, which is pretty, actually in real life, when you see the yellow light, it actually looks very dim. Okay, sangat lemah, because the electrons are moving at a very slow pace. Okay, they're not being accelerated because S2 is off. Okay, but this observation proves to us that light travels in a straight line. And how do you know that it's traveling in a straight line? Because the ones that are not being blocked by the Maltese cross gets to hit the pentafloor screen. But the ones that are blocked by the Maltese cross, okay, they are that's why you see the shadow here. All these are where the electrons tidak jadi menembus lah. Okay, because if light doesn't travel in a straight line, means dia boleh bend here and bend there, bahkan sepatutnya you won't get this image over here because light can just bend however they like. Okay, so this observation is very important for us, and it opens up a very important basics lah, okay, for our study in this chapter and in chapter 7 later. Okay, the fact that light travels in a straight line okay, has actually a lot of meaning in physics lah. Okay, for us it's like, okay, travel in a straight line like that. Okay, but actually light travels in a straight line has a lot of meaning in physics. Okay, it explains a lot of things lah. Okay, I'm not sure if you realize it or not by now, but it does. Okay, it does. And this experiment that involves the Maltese cross tube proves exactly that. Okay, the light travels in a straight line. That's why there is a shadow formed on the screen, because the electrons that hit the Maltese cross tube, they are stopped, okay, by the Maltese cross tube, just like what Wilson said just now lah. Okay, they are stopped by the Maltese cross tube and they cannot get past because they can only travel in a straight line. They can't like go there and then lepas itu memesong, tidak boleh. Okay, very important thing. Now, what if we turn on S2? So now you have S1 and S2. Okay, turn on. So there's a 6 volt and a 3 kilovolt power supply are connected. So we're going to have the electrons are now going to be accelerated. Okay, and what we find is we find the same dark shadow, okay, but it is now surrounded by a green light. Okay, and so this one means, okay, so electrons emitted are accelerated from the anode to the screen. The shadow is formed by the cathode rays blocked by the cross. That's normal. But the reason why it is green, it is because it's moving at very high speed now. Okay, take a look at before it was moving high speed. No high speed, it's just normal yellow light, which is the same color as, the light from the filament. But when you accelerate the anodes at high speed, you're going to get this green color screen. Okay, you're going to get a green color light, which is what we call the cathode ray. So cathode rays, like electrons, they travel in a straight line. And this green color that we see is called a fluorescence effect. Okay, they are the effect berpenda floor. Yeah, kesan penda floor. Okay, it's called a fluorescence effect. Okay, and so the Maltese cross tube okay, the Maltese cross tube. So these are pictures of, the cathode rays. This is already accelerated, means it is green color because there is an acceleration. So this Maltese cross tube, while it looks like a very amazing magic show, okay, but it tells us three very important things. Number one, the formation of the cross shadow shows us that cathode rays and electrons travel in a straight line. Okay. Secondly, the green color that we see, okay, tells us that cathode rays cause fluorescence. Okay, kesan panda floor, okay, a fluorescence effect. And thirdly, the cathode rays carry kinetic energy, which is converted to light energy when they hit the screen. Okay, let's talk about this for a little while. Okay, now we know that kinetic energy, okay, according to the formula, kinetic energy is 1/2 mv squared. And since the v is very high, because they are accelerating, okay, since the v is very high, when they hit the screen, the kinetic energy is going to be converted into light energy, which we will study in a little while. Okay, it's going to be converted to light energy. And so because of that, you know that all the kinetic energy, okay, is being converted to light energy, which is why we see the effect of the fluorescence on the screen. On the screen. Okay, so there are different types of Maltese cross tubes. There are some that are like this. Okay, it's just like pure vacuum inside. Okay, so the effect of the fluorescence is seen everywhere. Okay, this one, there is a dedicated screen at the end. So when you turn it on, and it will look like this. Okay, and this is what it looks like from, this is the same thing. Okay, this is what it looks like from the side view. And this is, actually we have this in the lab. Okay, so notice that there is the Maltese cross over here. And when the electrons are accelerated, okay, the ones that hit the Maltese cross, okay, will not be able to pass through. That's why we see the shadow on the screen. If there was no Maltese cross there, it'd be totally all green lah, bahkan. I mean, that's very logical. Okay, if there's no Maltese cross, it will totally be green. Okay, but the blocking of the Maltese cross causes the shadow on the screen. Okay, just like, if you stand, if the sun is behind you and you stand, and then you see your shadow, it's because the light, you are blocking the light. Okay, you are blocking the light. That's why there's a shadow over there. And the light that you are not blocking shows to us that light travels in a straight line. Also a very important thing, because if light can bend, kalau kita boleh membengkokkan cahaya, then there should be no shadow. And we will not be able to see any shadows in this world if light can bend. Okay, so we don't really think about this now when we see shadows. And we're like, oh wow, cantiknya. Okay, come, let's make the shape of a bird, the shape of a dog, the shape of a donkey, or whatever. But the idea behind the shadow is this, that light travels in a straight line. Such an important fact. Okay, such an important thing in classical physics. Okay, sorry, when we talk about classical physics, because in chapter 7 we're going to go into this thing called modern physics lah. Okay, which talks about bending of light lah. But for now, in classical physics, we know that light travels in a straight line. Okay, very important thing for us to know. Okay, let's watch this video.
Assalamualaikum rakan guru yang saya hormati sekalian. Di sini saya ingin berkongsi idea cara pemasangan tube palang Maltese. Video sebelum ni saya terangkan cara pemasangan tube sinar elektron. Ini adalah tube palang Maltese. Sebenarnya ada palang di tengah-tengah ni. Di tengah-tengah diperhatikan kalau ada palang sini. Sini pun dah flow. Tube palang Maltese ni masih mengekalkan prinsip kerja sinar elektron. Itu ada senapan elektron, plate pemesungan, kemudian skrin pernah flow. Okay. So untuk terpasang ni, kita pastikan sambungan kita ni pada 12 volt. 12 volt kita gunakan power supply. Okay. So, bila kita on-kan, kita akan dapati filament ini akan menyala. Dekat sini kita nampak ada macam cahaya sikit lah. Sebenarnya kaki ni ciptaan saya lah untuk mudahkan dia pegang. Sebab nak beli kaki ni saja harga 400 lebih. Jadi kalau kita buat sendiri tak sampai pun RM50. Okey. Bila filament ini dipanaskan, so elektron akan bergerak secara random lah. Nampak sini macam bayang-bayang. Cuma bayang ni tak sempurna lagi lah. So untuk bagi kita lebih jelas, kita pecutkan elektron daripada cathode ke sini. So untuk pecutkan elektron daripada cathode ke anode ni, kita wujudkan high voltage. High voltage ni kita sambungkan satu wire lain tambahan dan kita gunakan EXT voltage voltan lampau tinggi ni kita sambungkan. Okay, kalau kita sambungkan sini, berhati-hati jangan buat sentuhan. Okay, bila kita sambungkan ke sini, kita naikkan voltage ni perlahan sehingga kita nampak ada bayang hijau terbentuk kat sini. Kita naikkan, kita nampak. Oh, tak buka lagi. Oh, okey. Okey. Oh, saya terkena switch ni. Okey, kita buka perlahan. Kita buka perlahan sehingga kita nampak bayang hijau terbentuk di sini. Okey, bagaimana bayang hijau terbentuk? Ini pernah tanya dalam soalan SPM. Apabila elektron tadi dipecut daripada cathode ke anode, so elektron tadi akan melanggar palang. Bila elektron ni melanggar palang, so menyebabkan skrin kat sini kat sini berubah bentuk lah. Ada cas sikit sini. So rendahkan voltage ni. Okay. So, berhati-hati, kadang tersentuh ni ada cas mengalir pada badan kita. So, balik pada soalan tadi, bagaimana sinar warna coklat, warna hijau terbentuk. Apabila elektron dilanggar skrin pernah flow, maka dia akan tukar daripada tenaga elektrik kepada tenaga cahaya. So, bagaimana palang ni pula terbentuk? Palang ni terbentuk kerana elektron tadi dihalang oleh palang Maltese di tengah-tengah tadi. Okay, saya off kan, tunjukkan. Okay, dekat sini ada palang Maltese. So bila elektron tadi dihalang oleh palang Maltese, dekat sini akan menunjukkan palang. Okey. Okay, ada kesan apa? Pengaliran arus tapi kecil lah. Yang kecil pun bahaya pada pelajar. Okey, bagaimana kalau saya letakkan magnet dekat sini? Cuba lihat. Kalau letak magnet, apa akan jadi? Kalau letak magnet, palang ni akan bergerak ke bawah. Cuba lihat. Kita lihat palang ni. Cuma ada kebocoran current ni. Ada kebocoran current ni. Okey, bila kita letakkan dengan magnet, okey, dia akan bergerak ke bawah. Okey, untuk memahami bagaimana dia bergerak ke bawah dan ke atas, kita kena tahu hukum tangan kiri filament. Kalau elektron dia pecut daripada cathode kepada anode, berarti arus sebaliknya lah. Arus daripada anode kepada cathode. So ini pengaliran arus jari hantu kita ni. Kita lihat magnet ni, tak nampak sini magnet. So ini utara, ini selatan. Jadi magnetnya daripada utara ke selatan. Daripada utara ke selatan. Ini arus ke dalam. Ya. So magnetnya daripada utara ke selatan. So mengikut hukum tangan kiri filament, so dia akan bergerak ke bawah. Okey, ini pun pernah ditanya dalam soalan SPM berkaitan dengan tube palang Maltese, kenapa bayangan ni bergerak ke bawah. Okey. Okey, ini perkongsian mengapa dia bergerak ke bawah. Okay, bila elektron ni mengalir daripada cathode kepada anode, so arus akan mengalir daripada anode kepada cathode. So ini jari hantu kita adalah pergerakan arus. So ini adalah medan magnet daripada utara ke selatan. So bila kita rekatkan, dia akan bergerak ke bawah. Kalau kita terbalikkan, dia akan bergerak ke atas lah. Okay, dia bergerak ke atas. Okey, ini perkongsian daripada saya. Cikgu Idris, dan terima kasih.
Okay, just a short disclaimer. Is petua tangan kiri Fleming lah. Okay, I think he said petua tangan kiri filament, maka no, it's petua tangan kiri Fleming. But it's very important. Okay, we're going to learn this in a little while. So this is where Fleming's left-hand rule comes into play. When we introduce a magnetic field, okay, to the cathode ray, it's going to deflect. And the direction of the deflection is determined by Fleming's left-hand rule. Okay, and it is a much easier explanation compared to the one that you did in your flip grid video lah. Okay, but let's take a look at another video again.
Assalamualaikum.
This one.
Balik ke mana? Dia ke mana ni? Atas bawah?
Semalam cakap letak dua je ni.
Semalam cakap ke atas? Ke atas kan? Betul? Okey, cuba kita buat kat ni pula. Okey. Dia kena ni. Okey, ke mana? Ke kiri ke kanan? Kanan. Apa dah tanya?
Cikgu sama juga. Cikgu tanya. Sama. Boleh sama.
Ke kanan kan? Ke kanan cikgu. Ke kanan. Okey, terbalik pula.
Hijau. Kenapa mandu rasa?
Okey, dia akan bergerak ke belah sini lah.
Dia boleh kecil kan?
Okey, dah cukup. Dah, duduk
Hello.
Okay. I wonder how many of you, when you watch this video, you're like, oh, it feels like so long already that we haven't, like, sit together dan berhimpit-himpit. Yeah. Yeah, like so nostalgic kan. It's like, okay, jom kita tengok cikgu-cikgu sedang memberi demonstration and everybody gather in front and then everybody is like, oh. Actually, there is something that I don't get about this video lah. I'm wondering why the teacher put on one side and then after that the student go and put on the other side at the bottom. So it kind of balances everything out. So I'm wondering how come the deflection is not seen lah. Okay, because because of this one. Okay, I think it is neutralized by the second magnet lah. Okay, but the idea is this, that when you connect, so now we know that, okay, if we just turn on the 6-volt heater, okay, sorry, everybody is awake, so I can speak normally already. Okay, so when we turn on the 6-volt heater, 6-volt heater power supply, we're going to get yellow light. When we turn on the 3 kilovolts, the extra high tension, it's going to change into green color, proving to us that the electrons are being accelerated. Okay, and then the Maltese cross tube proves to us that the electrons or the cathode ray travels in a straight line. Okay, but the third thing that it proves, sorry, the fourth thing that it tells us, okay, is that when we put magnets, okay, at the sides of the tube, we're going to have a cathode ray that is going to be deflected downward. Okay, now again, let's explain this. Okay, so hold on. So the observation is this: the magnetic force is produced because the cathode rays carry a negative charge. Okay, an important thing that we need to remember is that the cathode rays are made up of electrons. Okay, that are released by thermionic emission and then accelerated. So all this is electrons work. And you know from chemistry that electrons are negatively charged. And because they are charged, they can be deflected by a magnetic field. So cathode rays can be deflected by the magnetic field, which is, sorry, I don't know which part of this is. Oh, okay, fine. So name the rule, okay, that is used to determine the deflection of the shadow between the magnetic fields. We use Fleming's left-hand rule, not S. Okay, Fleming's left-hand rule. Okay, over here. So, okay, this is the important thing. Because the electron is traveling from cathode to anode. Okay, anode is over here. Okay, so according to the left-hand rule is the current always flows from anode to cathode. Okay, this is where the current is flowing, but this is where the electrons are flowing. Okay, so you need to get this right now. Okay, current flow is always from anode to cathode, but electron flow is from cathode to anode. When we use Fleming's left-hand rule, we talk about current flow. We don't talk about electron flow. So the current flow is always from cathode to anode, and then you have the north at the bottom and the south at the top. So this is north, okay, this is north and this is south. So current flow is inside, okay, I mean, sorry, to the left. Okay, fine. If you follow the screen, current flow is to the left, okay, north is down, south is up, so it's like this. So the deflection of this is going to go towards the B. Okay, magnetic field is upward from north to south. Okay, current is to the left, okay, which is the opposite of the electron flow, okay, which is like that. And so the shadow will move towards B. Okay, this is a very, very important question. Again, using Fleming's left-hand rule. Okay, don't raise your right hand, everybody. Okay, so current is this way, magnet is this way, so shadow moves this way. Okay, towards B. So the direction, again, of motion is determined by using Fleming's left-hand rule. Now, what if we put the two magnets like this? Okay, we put one here north. Okay, this is the north and this is the south. So the magnetic field is from north to south. Second finger is north to south. Okay, current flow is always from cathode to anode, always going away from the Maltese cross tube. Okay, opposite from electrons. So it's this way. Okay, so where does the shadow move? Use your left hand and tell me, please. Where is the direction of the shadow moving?
Downward.
Okay, it's going to move downwards. Very good. All right. Same thing. Magnetic field is from there north to south, okay, to the left, north to south. Current is flowing into, current is flowing into opposite the electrons. Now you are seeing the screen. Okay, now you're seeing the screen. So the current is flowing into this one. Wow, so interesting. Where is the direction of the shadow moving?
Upwards.
Okay, the shadow is going to move upwards towards C. Well, so don't fall asleep. Okay, it's going to flow upwards towards C. Sorry, this way. That means the deflection tube is facing you. Okay. Sorry, my bad. Okay, so the shadow will move upwards, okay, towards C. All right. So that is the first one. The Maltese cross tube tells us 4 very important things. Number 1, cathode rays travel in a straight line. Number 2, when we accelerate cathode rays, okay, we are going to get a fluorescence effect. Okay. Number 3, the kinetic energy is converted into light energy. Okay, when the cathode ray hits the screen. Okay, so it's from electrical energy because we accelerate the electrons. So electric energy convert to kinetic energy for the acceleration, okay, which is converted to light energy when it hits the pendafloor screen. Okay, and the fourth thing is cathode rays can be deflected by magnetic fields. Okay, and so now since we're talking about deflection, pemesongan, we have to talk about deflecting tubes. Okay, and deflecting tubes are pretty easy lah. Okay, it's just 2 plates. Okay, 2 plates where one is a positive plate and one is a negative plate. Okay, 2 deflection plates. One is a positive deflection plate and one is a negative deflection plate. Okay, so what happens is if you connect a 6-volt AC power supply and then you connect the anode and cathode to a EHT1 power supply, okay, what you're going to get is you're going to get a straight line like this. Okay, there is no deflection. Why is there no deflection? Because the cathode rays is still traveling in a straight line. Okay, I suppose this is EHT1. Hold on. Yeah, sorry, this is EHT1. Okay, according to follow your diagram now. This is EHT2. Okay, it's just going to travel in a straight line because there is nothing happening here. This is still off. Okay, so this is proven since the beginning, travels in a straight line. Okay, now the next step is, the next box, okay, is if you, okay, I want you to take a look, sorry, okay, so this is the observation, people, in your jadwal kan, okay, in your jadwal, this is the observation. It just, totally no deflection. All you're going to see is just the cathode ray going in the straight line like this. Okay, let's take a look at this. Let me see if this helps you to understand what's happening.
Assalamualaikum. Di sini saya ingin tunjukkan tiub pemesongan sinar cathode. Saya menggunakan tiub pemesongan. Tujuan tiub ini adalah untuk mengkaji sifat sinar elektron yang boleh dipesongkan oleh medan elektrik. Kalau tiub palang Maltese untuk mengkaji sifat sinar elektron apabila ada medan elektrik. Kalau tiub palang Maltese untuk mengkaji sinar elektron apabila ada medan magnet. So yang ini untuk mengkaji kesan apabila ada medan elektrik. Okey, so biasa ada filament cathode, so ada anode dekat sini. So filament ini kita sambungkan pada power supply. Dekat sini kita perlukan dua ELT. Okey, agak panjang sikit, saya letak di belakang. Okey, ini kita sambungkan kepada ini kita sambungkan kepada filament. Kemudian kalau kita buka, so kita dapati ada nyalaan pada filament ini. So elektron akan terpancar secara random. So kita perlu wujudkan, ini off dulu. Kita wujudkan diagram elektrik antara filament ini, cathode dengan anode. Kita wujudkan antara ini dengan ini, kita wujudkan diagram elektrik. Ini cathode, ini anode. So kita gunakan ELT yang pertama, sambung kat sini. Okay. Apabila kita sambungkan yang pertama, kita buka, kita dapati ada nyalan, cuba lihat. Okay, ada nyalan warna hijau. Kita cuba tutup lampu, okay. Nampak ada nyalan warna hijau. Bukan warna hijau, warna biru. Warna biru. So, perhatikan kat sini. Okay. So bila saya dekatkan dengan magnet, sinaran tu akan terpesong. Untuk menunjukkan sinar elektron tu mudah dipesongkan oleh medan magnet. Okay, sekarang kita nak pesongkan sinar elektron tu dengan medan elektrik. So kita perlukan high voltage yang lain. Okay, katakan ini tersambungkan dengan terminal positif. Terminal positif dekat bawah ni. Sambung dengan sini. Ini terminal negatif. Sambung ke sini. Kita buka. Okay, kita buka. Kita pastikan. Okay, kita dapati sinar elektron tu akan terpesong ke bawah. Kenapa? Sebab bila bawah ni plate positif dominan, so elektron ni akan tertarik ke arah plate positif. Bagaimana kalau kita tukarkan? So kita tukarkan, cara dia ialah kita ubah suara sini lah. Okay, kita buka sini. Okay, bila kita buka ke sini, kita dapati sinar elektron ni akan terpesong ke atas. So, kenapa sinar elektron ni ada terpesong sikit, terpesong kuat? So, bergantung kepada arus kekuatan charge pada plate positif. Bila kekuatannya tinggi, dia akan terpesong ke atas. Bila kekuatan rendah, mungkin dia kurang terpesong. Okay, ini perkongsian daripada saya mengenai tube pemesongan sinar elektron. Terima kasih kepada Cikgu Idris.
Okay, sorry, another one. Oh yeah, sorry. This is the same one. Okay.
Kan? So, tunjuk ke apa? Sinar kathode. Gerak lurus kan?
Tadi minggu. Dah buka adik.
Okey dah. Dapat? Okey, so percaya? Kenapa colour dia pula?
Mungkin sebab dia screen.
Oh, that's it. Okay, so if you notice just now, I don't know if you noticed in the two videos just now, even when the EHT2 is not turned on, we find that the cathode ray is always seems to be going downwards lah. So I wonder if any of you can suggest to me an idea. Why do you think the electrons, even if we don't turn on the EHT power supply, the second one, okay, when we accelerate the electrons, why is it going down? Did you notice that just now in the second video? Let me. Any suggestion? Why do you think it is going down? Let me see. Okay, see in this case. So the EHT2 is not turned on, but we find that the deflect is still deflected downwards, Any suggestion? Why do you think that's happening?
Sebab
Earth. Okay, I think that's a very interesting. No, it's possible. It's possible. Not what I have in mind, lah. Any other suggestions? What do the rest of you think? Earth, yeah, could be drawn towards the Earth. Any other suggestions? I think Wilson, you said the same thing, right? Dibumikan ka? Is it? No other suggestion. Positive charge. No, but the thing is, there is no positive charge there yet. So over here there is no current flowing in here yet. So essentially, the cathode ray is just flowing. It's supposed to travel in a straight line, but instead of traveling in a straight line, it's just although this is turned off, this is still off. Belum lagi on. Kau tengok ni dah masih off. Okay, so if it is off, I mean, if it is turned on, then yeah, lah, it will follow, it will go towards the positive plate. Lah. Okay, but this is turned off, but it's still going downwards. What do you think? Okay, gravity. Yeah, I think it is possible. I think it is possible that there is a gravitational pull there. Okay, I think it's possible that maybe there is a, maybe it is being earth lah. Okay, although actually if you ask me, I think that the answer has to do with gravity lah. I would say gravity is pulling it down lah. That's why you see that it is going down, but it's going down very slowly because the gravitational pull is not very strong lah. Sebab dia sedang accelerating. Okay, if something is accelerating very fast, you know, even if gravity is pulling it, it's going to go down very slowly. Okay, but now we come back to this. So the second observation is if you connect the 6 volts, okay, to the EHT1 and the EHT2, you're going to find this one. Okay, if on top is positive and at the bottom is negative, okay, you're going to find the deflection goes towards the positive. Okay, and this tells us, okay, that the cathode rays are negatively charged. Okay, electrons are negatively charged. Cathode rays deflect in an electric field and negatively charged. And you can add down there, okay, please add down there. Lah. Okay, add down there and, oh, sorry. Okay, negatively charged and will deflect towards the positive, okay, plate. Always deflect towards the positive plate. Okay, and do you know that before people discovered this, before, this is a very amazing proof, you know. Okay, we always take for granted that, oh, okay, sudah menjadi fakta hidup bahawa elektron adalah negatif. But did you ever stop to wonder, how did they know that it was negative? How did they know that electrons are negatively charged? You know, what experiment did they do to determine that electrons are negatively charged? And this is the experiment that, you know, that kind of changed the whole world for us. Okay, when they found out that, oh, okay, electrons are negatively charged because they can be deflected towards the positive plate. Okay, we don't think about this because now to us it's just a fact. Okay, but when people didn't know this and they discovered this, that, whoa, okay, it's an amazing thing to find out that electrons are negatively charged. Okay, so that's what you're going to see. All right, let's take a look at the video that proves this.
So baru kita ada volta dan poli. Okey, bukan kita jadi apa? Akan positif kan? Positif. So sambung pada anode. Sambung pada anode. Alright. Tadi
Sikit lah.
Ini biar yang kedua. Pakai satu ya. So ini ialah cathode sambung pada cathode, anode sambung pada anode. So tak payah ada dua lah. Okay. Okay, dah tangan. Okay, okay, so sekarang kita dah ada perkara kuasa rendah, nak buat apa? Yalah, angkat untuk buat apa?
Sinar cahaya.
Sinar cahaya untuk buat apa? Nak buat apa? Panaskan filamen untuk?
Panaskan elektron.
So, pertama, hidupkan sekarang sudah panaskan filamen, panaskan elektron. Okey, hidupkan yang ini. Hidupkan ini akan buat apa? Menunjukkan elektron daripada cathode ke anode pergi ke screen. Nampak tak screen kali ni kat screen? Okay. Alright, then kita tengok apa yang akan berlaku. Dulu, aku screen okay. Alright. Dia kan terpeso.
Ada macam graviti ketarik pada anode.
Apa-apa?
So,
dah percaya? Percaya tak? Ha? Okey, sepatutnya dia straight kan? Tapi bila dia straight, tapi dia juga ada positif. Okey, terlajak dia. Biasa dia
Okay, so the video is just to show lah. So if we see the deflection going upwards, then you know that on the top there is a positive plate and the bottom is a negative plate. Now if we reverse it the other way around, okay, in this case, so now the top part is negative and the bottom part is positive, you're going to get this observation lah, okay, very normal, okay, which is the third observation in your table. And so the explanation is the path traced is still parabola, okay, it is still a curve, but it is deflected downwards towards the positive terminal. And we draw the same conclusion from it. The cathode rays deflect in an electric field and is negatively charged. Okay, so even if we change it, okay, it will still show to us the same characteristic, okay, which is it will sentiasa tertarik kepada plate positif. Okay, and here we have the same video again.
Hidupkan, obek.
Ke bawah.
Electron
Oh.
masuk.
Ini kita buat lama dulu setelah tak ada.
Cikgu,
Cikgu letak magnet
boleh ke cikgu?
Boleh tak ada. Cuba saya buat.
Ada cikgu.
Ada di kertas. Getar.
Ada saya cakap.
Dah. Cukup. Dah.
Main mana?
Okay, so obviously when you combine a magnetic field and electric field, there is going to be an effect lah. Okay, but you go whoa like that. Oh my goodness. Okay, so these are the characteristics of cathode rays based on these two experiments. The Maltese cross tube and the deflection plate tells us very, very important things about cathode rays and electrons in general. Okay, you need to understand this from a scientist's point of view. Before they discovered this, they didn't know anything. We already know this. Kamu sudah belajar bahawa electrons are negative, blah blah blah. And so this is like apa ini? Tahu sudah. Okay, but the discovery of this scientific fact, because of these two experiments, has a lot of meaning to physicists lah. Okay, in the whole world. First, it travels in a straight line. Okay, secondly, it possesses kinetic energy and momentum. Take a screenshot of this, people, because I need to go a little bit faster. Okay, thirdly, it's negatively charged. Fourth, it is deflected by a magnetic field and electric field. And fifth, it produces an fluorescent effect. Okay, when kinetic energy converts into light energy, when it hits the screen, it's going to convert into light. Okay, and so remember when I said just now that kinetic energy, the formula is 1/2 mv squared. Okay, something that you learned since Form 3 lah. So half mv squared, when it converts to light energy, how can we determine, the formula, okay, for light energy, which is what we want to talk about lah. Determine the velocity of electrons in a ray tube. We want to know how fast the electron is moving when it is in a ray tube. Okay, so let's go. So when a potential difference is applied across the cathode and the anode, the electrons will gain an electrical potential energy, which is called EV. Okay, this is electron volt lah. Okay, let me repeat. This unit is called, unit lah. It's called electron volt, which is also known as the electrical potential energy. Okay, so the emitted electrons will gain kinetic energy and will be accelerated to the maximum velocity, which is V. So the kinetic energy will change to light and heat energy when it hits the screen. Okay, so we're going to take a look at this. So energy changes in cathode rays tube. Okay, so the electrical energy E is calculated by the charge of one electron times the voltage that you supply. Okay, EV. Okay, so this is the formula for electrical energy, another formula for electrical energy, okay, which is electron volts. Okay, so when it comes to here, when it hits the fluorescent screen, it's going to convert into heat and into light lah. But we're not so interested in that. We're interested in how fast the velocity of the electrons is moving. Okay, so the electrical energy is going to convert to kinetic energy, which is half mv squared, which is then converted into heat and light. Again, we're not interested in this formula. Okay, we are more interested in this one, the electrical energy that is converted into kinetic energy. So this is in your textbook. Okay, just to let you know, the charge of one electron E is a constant. It's 1.6 times 10 to the power negative 19 coulombs. You studied this in chapter 3. Okay, but when we apply the principle of conservation of energy, if all the electrical energy is converted into kinetic energy, you're going to get EV equals to half mv squared. Okay, and this v squared is the maximum velocity of an electron, and we can calculate this just before it hits, okay, the screen. It's going to obtain a maximum velocity. And the good news is the charge of an electron is a constant. The mass of an electron is also a constant, okay, which you don't really have to memorize. Usually they will give you this. Okay, 1.6 times 10 negative 19 coulombs. You studied this in chapter 3. And 9.11 times 10 negative 31 kilograms. You studied this in chemistry. Okay, well, you should know this. Okay, so from cathode to anode, the acceleration is the motion. Okay, from cathode to anode, it will be accelerated because of the EHT over here. Okay, when it goes from the anode to screen, it will obtain a constant velocity. Okay, now in P, okay, this one, the type of energy is electric and potential. No, sorry, electric potential energy. Sorry, yeah, EV. Okay, EV. So from the cathode to the screen, it will gain kinetic energy. So all the EV will convert to half mv squared. And then when it hits the screen, it's going to be converted from light to heat. Okay, the main and most important thing is that the acceleration happens here on the first EHT. Okay, if I put the EHT over here, then it's going to accelerate all the way. But once it accelerates here, it's going to be constant velocity throughout. Fast enough. Okay, fast enough for it to hit the screen with a green color light. Okay, number 2, name the energy. This is electrical potential energy, okay, which is supplied to the cathode rays by the power supply between the cathode and anode. Okay, it's called electrical potential energy. Now, given that Q equals to E, charge for one electron, and V is voltage across the cathode and anode, the equation that relates the energy E, and V is this. Energy equals to the charge of one electron times the voltage across the cathode and anode. Okay, take note of this. Ini adalah voltan antara cathode dengan anode. Name the energy it gains by the electron when it accelerates from the cathode to the screen. It will be kinetic energy. And we know that kinetic energy formula is E equals to half mv squared. Okay, and if all the electrical energy, if all the electric potential energy is converted into kinetic energy, we have to assume the physics principle, which is the principle of conservation of energy. Okay, something that you learned all the way back in Form 3. Okay, so the equation that relates to both energies, oh dear, okay, based on principle is this, EV equals to half mv squared. The energy change is electrical to kinetic to light and heat. Okay, so electrical at first, when it is accelerated, it changes to kinetic energy, and then when it hits the screen of the electron gun, it becomes light and heat energy. Okay, so the voltage between the cathode and anode is 3000 volts. The charge of an electron is 1.6 times 10 negative 19. So you can count the kinetic energy, because the kinetic energy is also the same as the the electric potential energy, which is 1.6 times 10 negative 19 times 3000. You get 4.8 times 10 negative 16 joules. Okay, assuming the principle of conservation of energy. Okay, semua electric potential berubah menjadi kinetic energy. So dia punya nilai adalah sama. Okay. Now, if the voltage across the cathode and the anode in the vacuum tube is 4,500, what is the speed of the electron as it reaches the anode? Okay, so this one, okay, this is a very typical question. Okay, we have to assume, again, the same formula, EV equals to half mv squared, V kecil. And this is what we want to count. Okay, what is the speed of the electron when it reaches the anode, V2. Okay, and so what happens is we will get this. Okay, we calculate EV. and then we make it the same as half mv squared. Okay, when we make it the same as half mv squared, okay, so this is EV, 1.6 times 10 negative 19 times 4,500 volts. Okay, and we equate it to half mv squared. Okay, sorry, this is half mv squared. Okay, and since in a vacuum tube, okay, all the electrical potential is converted to kinetic energy, so we can calculate the V from this one. Okay, using the principle of conservation of energy. Okay, there are two extra examples. Okay, there are two extra examples that are found inside your textbook. Okay, but they pretty much revolve around the same thing. Okay, so the formula for this is very simple. It's just EV equals to half mv squared. You can even look at it separately. Electric potential is EV, kinetic energy is half mv squared. Electric potential always converts to kinetic energy, so we can determine the velocity of the electron based on this one, okay, based on the understanding of the principle of conservation of energy. Now, according to this formula, tell me the relationship between the voltage and the velocity of the electron. What is the relationship? Okay, the higher the voltage, the higher the thingy. Okay, fine. Okay, the higher the voltage, the higher the velocity. Very important relationship. You supply more energy for the electron, it's going to get more velocity. Okay, it's going to get a higher velocity. Okay, so your homework for today, I'm very sorry about this. Okay, your homework for today, and when I was looking at this, I realized that there is so few questions in the tutorial that it's not worth spending one class just for the tutorial. Okay, so your homework for today, and you know what, for the whole week. Okay, you don't have to hand it in today, but do it over the next few days. Hand it in before next Tuesday, is this tutorial 5.1. Okay, I think the questions there are pretty simple, and there's too few. Okay, I don't want to waste one entire hour just discussing this tutorial. So tomorrow, we will go into the next subtopic, but this tutorial, do it over the next few days and make sure you hand it in before next Tuesday. Okay, but next Tuesday is a holiday. Oh, sorry. Okay, fine. Then next Wednesday. So you have 1 week to finish this tutorial, because I think tomorrow, tomorrow I will not be able to give you another tutorial homework because 5.2 is a little bit long. Okay, so please finish up tutorial 5.1. You have 1 week to do this, okay, which is something that is very rare. So I hope 1 week is enough. Okay.